Assalamu alaikum. This is engineer Sadaqat Ali. So today this is my first presentation of literature review of conventional converters. Okay, so let's start the presentation. Okay, so why renewable energy sources are becoming more common today? According to International Energy Agency, which predicts that the energy consumption will be increased twice every year, and we know in order to generate the bulk amount of power, we mostly use thermal power plants. Which uses fossil fuels such as oil, gas, and etc. to generate bulk amount of power. But we know that in thermal power plants there is a huge amount of carbon dioxide emission in the environment. So keeping the carbon dioxide emission, we have to avoid using thermal power plants. So what is the way to avoid those thermal power plants and to use another technology, another resource that can give us a pollution free resource? And we know these are nothing but the wind turbine power plants and PV cells or solar plates. So using these technologies, we can basically generate power. We can basically generate power for utilization. But as we know that most of the windy areas are very far away from the residential area, like we know that in offshore side, the wind speed is very huge, so we can generate power over there, but we need to transmit that power from offshore to onshore. So you see here, these are some of the challenges that remote location of renewable energy sources like wind turbine, wind power plant that are installed very remote location, and stability issues will rise, and mitigating action must be taken while integrating renewable energy sources into the power system. And power balance must be considered and maintained through spinning reserves. So spinning reserve is basically those units in power plant. Those units are called as spinning reserves that are running but not connected with the power system. And using power flow batteries, we have to maintain the power balance. Because we know that renewable energy sources such as wind and PV panels depend upon the environment, depend upon the atmosphere. Like if there is no air, so no power can be generated through wind, or if there is or if the sun is not available, we cannot generate power from PV panels. So in that way we have to maintain the power balance, like we have to maintain the power demand and the power generated. So if for example, if the speed of the air is decreased, we cannot generate power at that time, so we have to utilize this spinning reserves, and we have to use some kind of batteries that can supply power. So these are basically the challenges with the while integrating, when we will integrate the renewable energy sources into the power system. Okay, since these uh, renewable energy sources are very far from the are very far away from the residential area, so we need a very efficient way of transmitting power from a remote area to the residential area. So we have two types of transmission. We know we have HVDC transmission and we have HVAC transmission. So if we see that HVDC has many number of advantages as compared to HVAC. Like HVDC has less number of conductors, so we can save the cost of the conductor. Even we can, using one conductor, we can transmit power from a very remote area to residential area, even using a single conductor. But in HVAC, like we have a three-phase system, so we need at least we need three conductors to transmit power. In DC, there is no reactance since frequency is zero, so the losses are very low in HVDC. But in HVAC, we have reactance. So basically, the losses are very high in HVAC system. In HVDC system, only active power is transmitted, but in HVAC system, both active as well as reactive power is transmitted. Yes, this is the very big advantage of HVDC, that you can transmit triple amount of power. You can transmit the triple amount of power using the same conductor in HVDC as compared to HVAC transmission line. So we see there are many advantages in HVDC system as compared to HVAC system. Okay, so if we are using HVDC system, then we need to control different parameters of the system in HVDC system. So the first one is the converter that we'll be using in HVDC system. Its dynamics, its steady state and fault condition. We have to control basically the steady state operation and fault condition. What if the fault occur near the what if the fault occur? So we have to control basically the converter parameters. We have to maintain the energy balance. We have to maintain the energy balance in the converter. Okay, converter must be controlled under unbalanced grid operation. Like if the load has increased suddenly, so what will be the impact on the converter of that? So we have to control basically the converter in that condition. We have to control and protect the converter under AC as well as DC network fault. We know fault can occur from both the side, from AC side as well as from the DC side. So we have to take care of that, and we have to control and protect the multi-terminal DC grids. MTDC stands for multi-terminal DC grid. So these are basically the controls that are needed, that must be ensured while using HVDC transmission line. Okay, now if we are using HVDC transmission line, we have seen that there are many advantages of using HVDC as compared to HVAC. So if we look at the different types of converters we have, let us first discuss that nowadays commonly used converter is MMC, Modular Multilevel Converter. Modular Multilevel Converter is basically nowadays the most efficient and the most reliable converter used in high voltage DC transmission lines. It has some attractive features such as built-in redundancy, higher efficiency, lesser harmonic distortion, means high quality of power. Okay, it is used in wind turbines and PV generation units, and it is mostly used linking offshore wind power plants for robust performance and minimal losses. So these are the two for robust performance and for minimal losses. Okay, so these are some of the advantages of MMC, but we have to look at other types of converters that we have been using in the past, and we have to see what were the what were the advantages of using those converters and what were the disadvantages. So we have to compare basically the different types of topologies available in the market. Okay, so let us come first and discuss what is basically a voltage source converter. We have two types of converter. One is called as voltage source converter and the other one is called as current source converter. So voltage source converter is used nowadays because of these attractive features, like it is the backbone of multi-terminal DC grids and super grids. Power electronic interface can be best implemented by voltage source converters, and it has the ability to impose voltage on AC side, and thus it can control both active and reactive power independently. So these are some of the attractive features of voltage source converters. So that's why nowadays voltage source converters are very common, and in voltage source converters, okay, so in voltage source converters we have if we see uh, in the past, two level converters were mostly used. It were used in industrial drives, home appliances, automotive drive system, and in low voltage grid connected converters, etc. Okay, there are different advantages of using two level converters, like they have less number of semiconductor devices, less number of semiconductor devices. So the losses are the switching losses can be very low, right? But there are many disadvantages of using two level converters. Like if we are talking about high voltage DC transmission lines here, so the switches has to bear a very high voltage. So using two level converter, if we are using two level converter, so this converter cannot bear that the high voltages at across its terminal. So two level converters are not used in high voltage DC transmission lines. Okay, so let us discuss the switching operation of two level converter, how two level converter works. So this is a typical two level converter. It consists of two switches with anti-parallel diodes. So we see here, in order to generate positive peak VD by 2, we have to turn on this switch, we have to turn on this upper switch, so the current will flow through this, and this waveform will appear, this peak will appear VD by 2 when the switch is turned on. In this time, the diode below connected with switch 2 is not conducting, but as the diode conducts, we see the voltage decreases from VD by 2 to minus VD by 2 as the switch conducts. In the next level, if the diode is only conducting, we see that the voltage level we are getting is minus VD by 2. But if the diode as well as the switch of the upper side is operating, we see that we are getting again from minus VD by 2, we are coming from minus VD by 2 back to plus VD by 2. And similarly, if the switch 1 is on, we are getting VD by 2. So using this phenomenon, basically, when the upper switch and the lower diode both conduct, we we have either rise in pulse or fall in pulse. But if the upper switch is on turn on, we will get plus Vd by 2, and if the lower diode is conducting only, we are getting minus Vd by 2. So this is basically the switching operation of a two-level converter. Now, there are many disadvantages of using two-level converter as compared to multi-level converters. So these are no doubt two-level converters are used. Two-level converters are economical solution for low power rating only. They are used in low voltage and low power applications up to 1 MVA. They are simple in structure, no doubt, since they have only two switches with few components. Harmonic component are around the multiples of the switching frequency. The harmonic components, the harmonic distortions will be very high in two-level converter as compared to multi-level converters. Okay, in converters using low power semiconductor, high switching frequency can be used, which mitigates this issue since only higher order harmonics will appear in the spectrum. Whereas in multi-level converters, are used for transmission lines, we normally require devices such as IGBT and MOSFET with blocking voltage. They have blocking voltage in kVs, so we require IGBT and MOSFETs. We used IGBT and MOSFETs normally in multi-level converters. Okay, switching of these devices cause losses. If the frequency is above 1 kHz, causes huge switching losses. So if the frequency is above 1 kHz, our switching losses will be very high. So normally in HVDC transmission lines, like if you talk about modular multi-level converter, our switching frequency is the fundamental frequency. So the switching losses are very low when we are using modular multi-level converter. Okay, so at low switching, more costly filters will be required to prevent harmonics causing damage. Series connection of devices required in high voltage applications. We know that. Okay, using two-level in high voltage application imposes huge stress on insulation. So this is the main disadvantage of two-level converter. And so in multi-level converters, we have a series connection of semiconductor devices, so the voltage stress is reduced. But in two-level converter, the voltage stress is very high. So this is basically a comparison of two-level converters with multi-level converters. Okay, there are other benefits as well. The blocking capability requirement of semiconductor valve is determined by the individual capacitor voltage rather than the full voltage DC link. Amplitude of the harmonics is reduced to high level frequency, since not all the switches are involved in every transition of the output voltage frequency at which the output voltage is changed can be increased without increasing the switching frequency. The first harmonic in the spectrum will appear at higher frequency where they can be more easily filtered out. So this is the main advantage of multi-level converters, that the harmonics are basically at the higher switching frequency, so they can easily be filtered out. Okay, if we conclude that using multi-level converters, more levels causes the harmonics to appear at higher frequency and are of less magnitude. So if we are using multi-level converters, our harmonics will appear at the higher frequency, so they can be easily filtered out, and if they are at higher frequency, no doubt their magnitude will be very less. Both of these effects contribute to reducing the amount of filtering needed to achieve the acceptable harmonic distortion. Yes, if the magnitude of the harmonic is less and they are at higher frequency, so we need a very less size of the filter to filter out the harmonic distortion. Okay, if the number of levels were to be increased further, an arbitrary accurate approximation of the reference curve would result. Okay, so these are the advantages of using multi-level converters. So you see here, if we see this, that if we have a two-level converter, so this is the switching waveform. So we see here in the frequency domain FFT analysis that our fundamental switching frequency is 50 Hz, and in two-level converter we are getting more harmonics near to fundamental frequency. And if we are increasing the level, let's say if we have a three-level converter, so we are getting, so we see that the amplitude of these harmonics reduces. And if we further increase the levels, such as 5 level, this is the 5 level waveform of the 5-level converter, so we see that the harmonics are very less and they are almost near to fundamental frequency, but they are of very low magnitude. And if we further increase the number of levels, like we have a 7-level converter, so we see that the harmonics are at the higher frequency, so they can be easily filtered out, and the size of the filter required to mitigate these harmonics will be low as compared to in 2-level or 3-level converter. So we see that if we increase the number of levels in the waveform, we will basically get the the amplitude of the harmonic distortion will be very less, and they will be at the higher frequency, so they can be easily filtered out, and we need a very small size of filter to basically filter out the harmonics present at the higher frequencies. Okay, according to literature, there are various types of multi-level converters have been proposed in the past. So let us discuss what types of multi-level converters are basically present in the market. Okay, so the first multi-level converter that we have is diode clamped converter. In diode clamped converter, the DC link is splitted by series connected capacitors. The DC link is split. We have to split the DC link into a number of according to the number of levels required, we have to split the DC link using capacitors, using series connected capacitors. Okay, so in this topology, in diode clamp topology, it is characterized by having diodes providing additional paths for current to produce additional voltage level. So that's why, since it has diodes that provides additional paths to produce additional levels, so that's why it is called as diode clamped converter. So you see, this is a typical diagram of a diode clamped converter. This is a typical diagram of a diode clamped converter. So let's discuss the working of a diode clamp converter. So this is basically a typical circuit for 3-level diode clamp converter. This is the total DC link. We have splitted this DC link using two capacitors. This is the VD by 2 and VD by 2. These are the two capacitors we have splitted. This is the neutral point. Okay, we have 4 switches, S1, S2, S3, S4. We have 4 anti-parallel diodes, D1, D2, D3, D4. So, and we have two diodes that are basically providing additional levels that are providing additional levels. Now, in order to produce the VD by 2 level at the output voltage, we have to turn on this switch S1 and we have to turn on this switch S2. So the current will flow from this capacitor to S1, following the path to S2, and this will be the path of the current. So we will get here the voltage level VD by 2. Now, in order to get the zero voltage, what we have to do, we have to turn on this switch S2. So the current will flow from this neutral point, following the diode, and from this switch, and will come out from this point. This diode will not be conducting. This diode S2 diode will not be conducting. D2 will not be conducting. This is a mistake here. so we will get a 0 level. And in order to get the minus Vd by 2, all the switches are off, so the current will flow from D2 D4 following the path to D3, and it will go here. So we will get minus VDC minus Vd by 2 level. Please note that in these three cases the current is going outward. Current is out of the phase terminal. This is the phase terminal, the current is out of that. Okay, likewise in this case the current is into the phase terminal. So when we will get the voltage Vd by 2, we will get it when the diode D2 and D1 is conducting. The current will flow into this terminal. And likewise, if we want to get the 0 voltage, so we have to turn on this switch S3. So the current will flow from this switch F3 following the path from this diode, and it will go into the neutral point. So this will be the path of the current for the 0 voltage. And if you want to get minus VDC by 2, so the current will flow from these switches S3, switch S4, and it will follow this capacitor and it will be grounded. So this is the path that the current will flow in order to get the minus VDC by 2 level. So this is the switching sequence for diode clamped converter. Okay, this is basically a comparison of 3 level and 4 level converter. 4 level and 3 level converter. This is basically a comparison of 3 level, 4 level converters. This is not neutral point clamp, but this is a diode clamped. This must be diode clamped DC, and this must be diode clamped. Okay, it was right. This is the neutral point clamped or diode clamped. Both are same. Neutral point clamp. So NPC stands for neutral point clamped. Okay, in 3 level neutral point clamped, these are mostly used nowadays since it has simple construction, but the harmonic distortion will be higher as compared to 4 level. Okay, in 4 level the number of diodes are increased. As we have to increase the level, so since we will increase the number of levels, so that diodes will increase. This is not used nowadays because it is much more complex as compared to 3 level neutral point clamp, and its cost is very high and mechanical design will be very complex. So due to the high cost and complexity, we avoid 4 level neutral point clamp converter as compared to 3 level neutral point clamp. No doubt the harmonic distortion will be very less, but due to the cost and complexity of the system, we avoid using 4 level and we used 3 level converters. Okay, this is the problem in neutral point clamp that previously we have discussed in the neutral point clamp. So there was a problem in that. Problem was that the losses are unevenly distributed. Like we have seen, we were using the 4 switches. The switch S1 and S4 have both switching as well as conduction losses, means the switch is turned on as well as turned off. But whereas S2 and S3 have conduction losses mostly. They have mostly the conduction losses, they don't have the switching losses. They are very their turn on and off period is very low as compared to switch S1 and S4. So the losses are unevenly distributed. Now to mitigate these losses, basically to distribute the losses unevenly, we have the literature have supposed active neutral point clamped capacitors, active neutral point clamped topology. So this is the topology, active point neutral clamped. This is the topology. Now using this topology, we can not only generate the zero level in many ways, but our losses will be uneven losses can be avoided using this topology. So if the losses are concerned, we can use the active point neutral clamped, and we can avoid the normal NPC, and we can use APC. So this is all about the diode clamped. See, this is all about the diode clamped converter. So we see it's working. We did discuss the different types of converters and what are their advantages and disadvantages and why they are not used. And we did discuss that what are the problems in previous technology. So we did see how it can be overcome. Okay, now let us come to the next topology, that is basically called as a flying capacitor converter. So in this type of converter, we have connected a capacitor here. Both the midpoints through which the switches are connected, these points are basically connected through a capacitor. So that's why it is called as a flying capacitor topology. So let us discuss its working. So this is basically a typical working diagram of a flying capacitor. So we see in order to generate the positive voltage VD by 2, we have to turn on this switch S. Let's call this switch is S1 and this switch is S2, similarly S3 and S4. So in order to produce the output voltage VD by 2, we have to turn on this switch and this switch. So this will be the path of the current. So the current will flow from this switch S1 and it will come here S2 and it will leave this phase, out of phase. So we will get the voltage VD by 2. Similarly, in order to get the zero voltage, how we are getting the zero voltage, that this is the potential VD by 2 here, and this is the potential, this capacitor, we are assuming that this capacitor is fully charged, right? So if this is the direction of the current, so the current will flow through this capacitor, and the capacitor will have all the potential across it. So the no potential will appear across this point. So if there is no potential, so we say that there is a zero potential across this point when this switch S1 is on and the current is flowing through this capacitor. Similarly, the other way to get the zero potential is to conduct through this diode. To turn on this diode, if this diode is on, so the current will flow through this and following the path of this capacitor. If the switch is on, so from this switch current will flow here. So the overall voltage is 0 and we are getting here a zero voltage, a zero potential. Similarly, in order to get the minus VDC by 2, both the diodes D3 and D4 are conducting and the current is flowing through this terminal. So we are getting minus VD by 2 here in this sequence. So this is the switching states of a 3-level flying capacitor converter with AC current directed out of the phase leg midpoint. Okay, there are some drawback of the flying capacitor. It says that theoretically number of levels can be increased and realized, but in practical, if the levels are increased, the circuit would be very complex due to the increase in flying capacitors. Definitely, if we are increasing the number of, if we want to increase the number of levels so that the power quality of the converter is more, we have to increase the number of flying capacitors. And if we are increasing the number of flying capacitors, our circuit will be very complex. And this complexity, and it says that insulation problem may arise since the capacitors need to be separated to avoid any flashover. Here we are talking about the high voltages. So in high voltages, the capacitors must be insulated so that there may not occur any flashover. So we have to basically we have to insulate the capacitors from each other so that the no flashover occurs. So if we are in order to insulate those capacitors, uh, the cost of the converter will definitely increase. So the cost of the converter will increase, which depend upon the energy that a capacitor can store. So obviously, if we are using a capacitor whose energy is very high, so its cost will be very high, and insulation, to provide insulation to those capacitors for higher number of levels, the cost will definitely be very high. So because of this reason, flying capacitors are have made less success in the market as compared to neutral point clamp. So due to this issue that we cannot increase the number of levels because of the insulation problems and because of the production of flashover voltage, the flying capacitor is not used nowadays, or not used, or not have made that much success in the market as compared to neutral point clamped converters. Okay, so what are the benefits of the multi-level converters? Here we are talking about the converters that have submodules in its overall structure. So levels can be increased by series connection of the submodules. Complexity will be very less as compared to neutral point clamp and flying capacitor. Here we are talking about the modular multi-level converter. We are going towards it, and ultimately the power quality will be improved. So if we compare the neutral point clamped and flying capacitor with modular multi-level converter, it says that in neutral point clamped and in flying capacitors, you cannot basically increase the number of levels since the complexity will be very high if we are increasing the number of levels. But in modular multi-level converter, complexity, we will see that the complexity is not increasing because of the series connection. In order to increase the number of levels, we have to connect the different submodules in series. And similarly, if the number of levels are increased, ultimately the power quality will be very high. So this is the reason that nowadays modular multi-level converter is taking much more interest of the researchers, and is nowadays used in high voltage DC transmission lines as compared to other typical multi-level converters that utilizes neutral point clamped and flying capacitors. Okay, so the submodule can be made using the submodule can be half bridge submodule and it can be full bridge submodule. We will discuss both of the topologies individually, what is half bridge submodule and what is full bridge submodule. Okay, so this is a typical half bridge submodule. It consists of two switches with two anti-parallel diodes and a capacitor connected in parallel across them. So this is a typical operation of a half bridge submodule. It can be realized with this equation. V naught is the output voltage and it is equal to S times, S is the we are calling S as a variable if this variable is 1, if this for example, if this variable is 0, we will get 0 output, and if this s is 1, we will get the output, that is basically the capacitor voltage. So this is a typical operation of a half bridge sum module. So if the switch, if this value, if the value of this s is 1, we will get a positive voltage, and if it is 0, we will get nothing in the output voltage. Okay, this is a half bridge sub module. So let's see the full bridge sub module. So this is the full bridge sub module. It consists of total of 4 switches with 4 anti-parallel diodes and 1 capacitor connected parallel across them. Okay, its operation can be realized with this equation. This equation is basically V out is the output voltage, is equal to S1 minus S2 into Vc. Here S1 is S1, if the S1 is 1 and S2 is 0, if we put the value of these variables into this equation, we are getting the voltage plus Vc. And if the value of this S1 is 0 and S2 is 1, we are basically getting the value minus Vc. So you see here that, and if both the values S1 and S2 are 0, we will get 0 output voltage. So you see, using the full bridge sum module, we can get the number of 3 levels. We can get 3 levels, but when we were using the half bridge sum module, we will only be getting the positive voltage, which is Vc, and if S is 0, we were getting 0. So the number of levels in full bridge modules are basically more as compared to half bridge sub module. So if we compare half bridge sub module and full bridge sub module, so it can provide only unipolar voltage half bridge, but whereas full bridge sub module can provide bipolar voltage, since we were getting two voltage levels like VDC and minus VDC, but here we will only be getting only positive voltage. Okay, the half bridge sub module can provide n plus 1 levels, like we were getting VDC at 0, but full bridge sub module can provide 2n plus 1 levels. Like if we are using only one sub module, so if we put n is equal to 1 here, we will get 3 levels. Similarly, it is more costly to get the same level as compared to full bridge, but it is less costly since the number of capacitors needed will be reduced. And half bridge can provide average voltage in the range of 0 and VDC, whereas a full bridge can provide twice the voltage level of half bridge. So this is the big advantage of full bridge over half bridge, that it can provide twice the voltage of the half bridge as compared to full bridge. So this diagram shows that this is the half bridge, this is the average voltage that the half bridge can provide Vc by 2, whereas the full bridge can provide twice the voltage of the half bridge. So this diagram proves that the full bridge topology is very much cost effective and is very much has many advantages as compared to half bridge topology. So we are ending here this presentation. We discussed that why nowadays renewable energy sources are used, and if we are using the renewable energy sources, so what type of network, using what type of network we can transmit the power efficiently. So we basically conclude that HVDC has number of advantages as compared to HVAC, and then we discuss that when we use two level converters which has 2 level, and we did discuss that what are the multi-level topologies that were used in the past, like we discussed about the diode clamped converter, we discussed about the flying capacitors converter. So these topologies were used in the past, and we conclude that, and we did see that in Newton point clamped, the losses were unevenly distributed. So to avoid that problem, we used active neutral point clamp. So in that the losses were not that the losses were evenly distributed to each and every switch. And we did discuss about the flying capacitor, and moves on. We discuss about the half bridge and full bridge submodule, and this is all about for the today's presentation. uh, we will continue from this in the next video. Till then, Allah Hafiz.